Hi, welcome to this session on the challenges of coherent mesh network development. This is a joint presentation as part of a long partnership between Arm and Cadence. My name is Dave Conan. I'm a senior product marketing manager at Arm, managing a line of interconnect products for the infrastructure group for servers, networking, and high-performance computing. Today, Nick Heaton from Cadence and I will be providing an overview of Arm's Coherent Mesh Network interconnect and Cadence design tools to overcome some of the challenges in producing a scalable, performant SoC interconnect. Nick will be presenting in the second half, and I will begin this interview. I'm going to start with a big picture of where Arm is going with IP for SoC design and interconnect to support them. Our architectural strategy is around anticipating the workloads of supporting trillions of devices. It's going to be a significant change from today's billions of devices, which are mostly cell phones. In that, the data flows currently largely downstream from cloud data centers towards those devices. And most of the data is video. In a world of 1 trillion intelligent devices at the edge, most of the devices will be IoT meshes of sensors and other devices, and each producing their own data. The massive increase of data generation at the edge will shift the balance of data flow from downstream to upstream, requiring development of smart filters at the edge. The SoC interconnect needs to accommodate different scales of SoC devices and still maintain low power and high performance. There are some challenges to building these devices, which we'll be touching on in today's presentation. For these different size SoCs can have a range of compute elements and accelerators either in or on connected to the interconnect. There'll be a mix of CPUs, NPUs, GPUs, ML, crypto, I/O masters that can attach to a variety of memory, cache, and other configurations. The interconnect must maintain cache coherency for hundreds of CPUs and I/O and accelerators. And we'll have also multiple chip connections with different topologies to support and PCI Express and so forth. The interconnect must be, like I said, efficient, scalable, low power, and minimal area in these SoC designs. The interconnect we'll be talking about today is Arm's latest CMN-700. It's the third generation of coherent mesh networks for supporting the latest Neoverse N2 cores and also our previous 3 generations of cores as well. The CMN IP is not like other RTL IP in that it's not a fixed configuration, but rather a composable from a set of subcomponents. We have a GUI for a mesh configuration tool called Socrates that enables you to assemble subcomponents and crossbar elements to create a topology that's right-sized for your chip. Going clockwise around this diagram, you can see that there are various subcomponent device types that attach to the mesh, like CPUs, accelerators, I/O, chip-to-chip, memory. There are also several build time options for increasing the data width or number of device ports per crosspoint, cache sizes, buffer, queue depth as well. And Arm also export this configuration that you create in Socrates to a CMN performance simulation model so that you can add traffic generators and dummy slave nodes to experiment with optimal component placement during your architectural phase. Some of you may be familiar with our public release information on the CMN-600. And relative to that, the CMN-700 is just more of everything. CMN-700 is a step function in capacity, performance, and feature set. It allows for a composable interconnect that right-size for your SoC with industry-leading performance power per watt. You can see from this diagram that we've increased the number of CPU cores from, say, 64 and to 256, a 4x increase in overall system as well. We've increased the number of system cache elements from 32 to 128, and also the size of those. We've increased the number of device ports that you can connect to cross points. We've increased the width of the interconnect, AXI and chip-to-chip interfaces, a number of memory controllers, and even reduced the latency for chip-to-chip interfaces. As a general guideline component placement, we advise placing the system cache, or also known as a home node, and CPUs together around the interconnect and place the external memory controllers and I/O on the outer edges. This provides the lowest average latency and good load distribution. For small configurations, like on the right-hand side, one could place the CPU clusters and cache outside the mesh fabric. The example here shows XPs at the center with a very short mesh lengths between them. And there are like 4 system caches and Snoop filter instances in green and 2 CPU clusters on the bookends. For slightly larger arrangements of 16 to 32 CPUs, the example in the middle allows system cache and Snoop filter instances to be placed within the mesh itself, with CPU clusters and I/O on the periphery. This increases the mesh link area just a bit. Lastly, there are larger configurations and higher core configurations. We'll be advising grouping the CPUs and home nodes around a cross point as a tile. Then these CPU H&F tile templates can be replicated with parameterized signals and duplicated for a larger mesh, as shown on the example for the AWS picture below. Memory and I/O should also still be placed on symmetrically around that mesh to provide good balance and distribution of cache memory request and response times to minimize congestion. Those single mesh configurations on the previous slide can be expanded with CCIX and CXL gateways to connect to other dies or multi-chip modules or some other accelerator or memory expansion modules. Both CCIX and CXL protocol provide multi-chip cache coherency connectivity, but their features and capabilities are different enough to maintain both. CCIX has a rich set of coherency operations that make it better suited for distributed cache Snoop filtering across several identical heterogeneous devices, whereas CXL's host-based coherency policy allows one to make simpler memory expansion models and accelerated devices. We've worked with Cadence to define a CMN to CXL interface called CXS issue B that can be based, it's based on CXL flits. And the gateway and CXS protocol support multiple modes of operation, including an SMP mode to transport CMN transactions, GIC interrupts, and core site debug information between the chips. Cadence also provides a rich set of PCI, root complexes, DLLs, PHYs for both chip-to-chip and socket-to-socket signaling. CMN has included multi-chip SMP for 3 generations, where the system cache is associated with its shared local memory. The CMN-700 will offer a new hybrid system cache feature that reduces average cross-chip latency and bandwidth by allowing a portion of the system cache to store remote memory accesses. This reduces the frequency of requests going to the other dies. We've also introduced support for separate CPU cache chiplets to connect to centralized memory I/O hub for a uniform memory and I/O access patterns. It also allows for a mix of process technology between chiplet and hub. As mentioned before, it may take some experimenting to optimize component placement. Socrates configuration tool is an icon-based GUI that lets you select mesh sizes, device types, cache sizes, and drill down into the details of sizing and enumerating those elements. With the Socrates configuration tool and perf simulation model, you can narrow in on the optimal topology and configuration and build time options. When finished, the Socrates tool ensures the export of CMN RTL is error-free and compliant with AMBA standards like CHI, AXI, ACE-Lite, so that you can connect your Neoverse CPUs, accelerators, memory, and I/O components with confidence. As mentioned, as a transition, to Nick's talk, I would like to note that the CMN mesh operations operates at one frequency, but has many asynchronous bridge elements for connecting to other clock domains like CPUs or memory controllers or I/O bridges. When a mesh gets over a certain size, it becomes challenging for the clock tree branches to become synchronized with all of the cross points and elements. To help with this, the CMN introduces an asynchronous mesh credit slice, so one can partition the mesh clock tree into, say, 2 or 4 clock subdomains or quadrants. This helps with the clock skew one sees at the edge of the separated quadrants to help meet clock skew and setup time. There's also much more that can be done with Cadence tooling as well. That is what Nick Heaton will be talking about next. So I thank you for your attention, and you can send your questions to me at the email shown at the last slide of this presentation. I pass it on to you, Nick.
Thank you, David. Hello, everybody. My name's Nick Heaton, and I'm a distinguished engineer in Cadence R&D, responsible for SoC verification. As David has shown, the Coherent Mesh Network is a powerful and highly configurable IP delivering leading-edge capabilities. These capabilities and configurability, however, put the onus on system integrators to validate a multitude of parameters relating to function and performance. The rest of this presentation provides an overview of the kind of challenges facing CMN-based system integrators and how Cadence System VIP solutions address those challenges. So firstly, let's discuss some of the key challenges. Looking at the CMN IP itself, there is a need to validate that the component has been configured correctly. Are the point of coherency queue depths the right size? Is the snoop filter and system level cache correctly sized? Is the memory map as expected? If your system uses coherent accelerators via C6 or CXL connections, then you'll also want to validate that coherency is maintained between the CMN and the coherent device. This can be done in RTL simulation using Cadence Accellera and verification IP, or you may prefer to run coherency tests on the embedded cores in the cluster, which may come at a cost of runtime performance, and hence you may need to use simulation acceleration with dedicated acceleration hardware, such as Cadence Palladium. The CMN works closely in combination with the memory controller or controllers you plan to use, and so also validating the system memory performance of the two IP together is critical to ensure that your performance issues aren't baked in. It's far easier to test and debug just the CMN and memory controllers as a subsystem than it is to do the same on the full SoC. However, that does require synthetic traffic generators to model the system behaviors and exercise the full range of scenarios. If your system includes a PCI Express controller, which is very often the case, then it will be probably configured to operate with a system MMU. And it's key to validate the function and performance of the combination of CMN, memory, SMMU, GIC, CPU clusters, and the PCI Express controller all together. This is a complex setup which requires considerable embedded software and as well a controllable endpoint such as a VIP or an accelerated VIP. And all of this is needed to explore features such as address translation services, TLP processing hints, and such like. PCI Express also introduces the challenge of ordering and deadlocks. Running scenarios to stress the system and validate that there are no issues is absolutely imperative. So how do we approach all of these challenges? Conceptually, it is simple. We need a number of test benches to address the challenges at each level, and we may need to do that at the right level. Finding and debugging issues is always more productive with the minimal subset of IP possible. However, some of the challenges can be addressed directly using just the CMN IP, but a lot of the challenges we've talked about need to be addressed with other IP integrated. In this diagram here, we see an example of a test bench with just the CMN. It requires instantiation of verification IP or accelerated verification IP based on the simulation mode you're using, along with a scoreboard to check that there is correct behavior, as that must be checked across all of the coherent interfaces. This kind of test bench can be built using UVM methodology for simulation or in C for maximum performance using an accelerator or an emulator. As CMN can be configured with a large number of ports, there can be a lot of work in building these kind of test benches manually. The Cadence System Test Bench Generator addresses this issue by automating the generation of these kind of complex test benches. The next step, once a test bench is built, is to add comprehensive stimulus. This is easier said than done, especially if you're creating coherent use cases, which are further complicated when PCI Express is added into the mix. Also, creating performance use case content is pretty tough, as there is a need to model coordinated traffic threads on multiple interfaces. An industry standard solution to the use case creation challenge is the Accellera Portable Stimulus Standard, PSS for short, which provides a method for modeling system behavior and dependencies in an abstract way, which can then be used by tools such as Cadence Perspec to generate a fully formed scenario from the abstract use case model, and uses a constraint solver. By providing libraries of content for specific challenges such as coherency, performance modeling, and PCI Express, the users get a powerful jump start to create complex content right out of the box. Here we see how adaptive traffic profiles, which is an Arm specification, are included in the System VIP performance library, and they can be dragged and dropped to form a use case with fields that can be left unconstrained or constrained, giving the potential to generate multiple system tests from one use case. In some ways, this is analogous to UVM constraint solving. However, the granularity of randomization in PSS is much larger than the fine-grained clock-by-clock randomization used in UVM. PSS is designed to be targeted at exercising paths through an SoC rather than exhaustively exercising interface protocols. Once we have Testbench and test content, we can run tests and analyze the results. In the case of system function, we can use the widely available approach of functional coverage to visualize test completeness. However, for performance analysis, there is a distinct gap in tool support. Cadence System Performance Analyzer allows results from any test case to be inspected from a performance angle. The graphs we see here are for two different CMN configurations. The first on this slide is for a minimum configuration, and on the next slide we'll see the max configuration. And we're comparing the performance using an adaptive traffic profile performance use case, very quickly created, and then we can view the results graphically. The only difference between the minimum and max configuration in this example is the read acceptance setting, which is configured through Socrates, as David showed earlier. The first set of charts here is for a read acceptance of 32, and it illustrates three key parameters: bandwidth over time, latency over time, and outstanding transactions over time for a mixed read-write traffic use case. Outstanding transactions are a computed metric indicating the difference between transactions issued and transactions completed, and this is very useful, an indicator that can be used as a proxy for congestion in your system. Notice the max bandwidth in the first case, in the minimum, is about 6 gigabytes per second, and the runtime is 12 microseconds. Outstanding transactions are roughly steady at 45. If we now step to the max configurations, we now have a read acceptance of 256. We see that we achieve peak performance of 32 gigabytes per second, so dramatically improved performance until all the read transactions have been issued, and the OT peaks at 64. So we can start to get clues about whether we've configured our CMN adequately for the use case that we're expecting. And what we're trying to do is avoid introducing excess hardware which may be redundant for our particular use case. The next two slides show a purely read-only case, and again show how read acceptance of 32 does throttle the read performance, and that setting it to 256 resolves that issue as the bandwidth requested, which is 32 gigabytes a second, is actually achieved in the second chart. These graphs are a small window into the kind of analysis that can be achieved, and typically these kinds of tests are run on CMN to validate configuration and then run with the DDR controllers attached to ensure that the combined performance of CMN and DDR are matched and don't introduce any inadvertent bandwidth throttles. So coming back to our challenges, We've seen that the challenges we talked about at the beginning of the presentation are addressed by 4 key system VIP components. We have Testbench automation for creating simulation and acceleration test benches. We have a verification scoreboard which supports runtime and post-process scoreboarding and correlation to ensure coherency correctness. The third piece is system traffic libraries, which are reusable content to support coherency, performance, PCI Express, to name just a few. And then finally, we've seen System Performance Analyzer, which provides comprehensive on-chip bus and DDR analysis to ensure your system performs correctly. With these purpose-designed tools and content, users can be confident that adopting leading-edge IP like CMN can be undertaken with the confidence that Arm and Cadence are working together to ensure SoC development challenges are fully addressed through System VIP. If you have any questions, please submit them and we will come back to you after the event. So thank you for listening, and goodbye from myself and David.